we're talking naming, I think. And this is back to chapter 3, last part of chapter 3, which should be naming. So last time we covered a number of different types of really ionic sort of naming. So we do have our type 1, which is a metal and a non-metal. And whenever we have a metal involved, as we talked about, it really is the most important thing. And in this particular case, a type 1 metal is one that has a fixed positive charge. And that's pretty much your group 1, 2, 3, your zinc, cadmium, or silver there. And because they do have a fixed positive charge, we don't have to worry about anything other than basically naming it. And we use the whole name of the metal. We give the non-metal, we drop the last part, maybe a little bit more than the last part, and we do replace it with an IDE in this case. We also have type 2, which is sometimes referred to, which is also ionic, and also a metal and a non-metal together. And once again, here it is that metal that sort of predicts how we should go about naming it. This type of metal, though, has a variable positive charge. And that's essentially going to be a transition metal, except for obviously zinc, cadmium, or silver. Or it will be just to the right there on the periodic table, again, where we have things like lead and tin and that sort of area underneath the staircase. In this case, because it can have multiple charges, the metal, we do have to include a Roman numeral, and that is what the Roman numeral indicates. Again, not how many metals or anything like that you have, but it is, if you took one of those guys, the positive charge that you would have on that metal. And we pretty much name it the same way. We go a whole name again of our metal. We still do, again, our non-metal with the IDE treatment. And again, in between there is going to be our Roman numeral. And again, that is the positive charge on the metal in this particular case. The way that we can figure out the charge there on that transition metal or that type 2 metal is essentially it will always be attached to something that you know the charge of. As the negative guide pretty much, and you can kind of work your way backwards and figure out what the charge is, and that will get you basically what the Roman numeral will be. Remember that there is absolutely positively no prefixes here in any of these two types of naming, and that means if you have multiples of something, it will have no effect on the name. You just follow basically this pattern. We finished up, I think, last time talking about polyatomic ions, and polyatomic ions are groups of nonmetals that have charges. So they are interesting things. They are basically covalently bonded and sharing of electrons, which is why they never really break apart into individual sort of elements. They move around as groups because they are sharing electrons. They're really bonded to each other. But overall, because of who they're bonded to and the distribution of the electrons, it does end up having a charge. So most of the polyatomic ions are negative, and most of them will end in either 8 or 8. And again, 8 is the most oxygen, is how those guys should end, and 8 is the least oxygen. So as we talked about, you could kind of group them up in a sense by groups of 2, for example, that are related to each other. Everything else will be the same, the charge. The only difference is the number of oxygens. And as I mentioned last time, sometimes a good way to do it is just maybe remember all the 8s and know that the 8s are just 1 oxygen less, or vice versa. You can learn the 8s and know that the 8s would be 1 oxygen more. There's also groups of 4 that are related to each other, like ClO4 minus, we saw ClO3 minus, ClO2 minus, ClO minus. And again, in a group of 4, we still follow the same pattern in terms of how they end, but we do add something to the guy with the most, and that's per, for example, here, chlorate, so ending in 8 and starting with per. This guy would be just chlorate. This would be chloride, as it has the least amount of oxygens, and the guy with the smallest amount of oxygen in that group of 4 will also end in ite, but start with hypo, right? And that'd be chloride in this case. In addition, a couple of other things that we do, you can put like a hydrogen or an H plus in front of a polyatomic ion and it becomes hydrogen, whatever it may be. So again, if we had something like our HCO3 minus, that is really based off of CO3 2 minus, which is carbonate. And since we put that hydrogen in front, it is known as hydrogen carbonate, as we basically added the H plus to it. And in addition, hydrogen carbonate is sometimes just referred to as bicarbonate without the hydrogen sort of mentioning. Also happens with things like sulfate. If you put hydrogen in front of it, it is hydrogen sulfate or bisulfate. If you put 2 hydrogens in front of 2 H pluses in front of a sulfate, it is dihydrogen sulfate. Those are some other things. In addition, there are some polyatomic ions that do end in IDE, like hydroxide, cyanide, azide, for example. So there's a number of them that do end in IDE, but a vast majority will end in the H or the ite sort of configuration when you do it. One of the few polyatomic ions that are positive is NH4 plus, which is the ammonium ion. And this is one of the few positive ones. There's a couple of others, but what we found and talked about at the end there as well is most of the time you will probably have your polyatomic there, maybe ion hooked up with a metal in most cases. And once again, what that usually will end up doing is we will fall back to really our type 1 or type 2 rules, because again, all you have to remember is metals involved. So that is what we should look at in terms of how to name it. So we'll either need a Roman numeral or no Roman numeral, right? And depending on if it's type 1 or type 2 sort of compound. In terms of the polyatomic ion, they're pretty simple in the sense, once you learn them, is you just use basically the whole name of a polyatomic ion. And again, it does not matter if you have more than one of them, you just use the whole name. The thing that does matter when you have more than one polyatomic ion is when you're writing formulas, you do need to put parentheses, right, around a polyatomic ion and a number on the bottom to indicate how many of each of those that you have. Other than that, if you just have one polyatomic ion, you do not need the parentheses. You can just leave it, like something like this. In this case, so if you had something, say, like that, you would have a parentheses. Any questions on any of that stuff we talked about last time in terms of naming? You're asking how many? Like what? It would be in the case of carbonate. It would be in the case of carbonate, if you attach 2 hydrogens, you would actually get carbonic acid, which is neutral in that sense. But adding just 1 hydrogen, which is H plus, the -2 and the +1 leaves you still a -1 over. So it won't become neutral at that point. So with the hydrogens, yeah, so for the most part, things that have a negative charge, and I would say sulfate, carbonate, phosphate are very common ones that can kind of do that. And the truth is, it's really derived from this guy right here, which is an acid. So H2CO3, when it, actually, I'm going to do it on the next page here. Oops. Go this way. So something like H2CO3 is actually a weak acid, and when it breaks apart, it will lose one hydrogen and make HCO3 minus. And something like HCO3 minus can also lose one hydrogen and make carbonate. And as you'll learn in 200B, if you take it, these guys are what are referred to as acid conjugate base pairs, and the difference is always one hydrogen. So this guy is still an ion. This guy is actually an acid in this case. And then these guys are both obviously ions in that case. Yeah. Other questions? So speaking of that, nice transition. Let's talk about acids and how to name acids here. So acids are really any substance that can produce H plus in solution. So really in order for something to be an acid, and when you talk about acid-base chemistry, one thing that you'll learn is H plus and H3O plus, which is the hydronium ion, also a polyatomic ion. They're essentially the same in sort of acid-base chemistry. So sometimes you'll see people talk about an acid as being able to produce H3O plus in solution, but H plus, H3O plus are essentially equivalent to each other. And what makes something an acid is the ability basically to do that. And what we're talking about is the ability to just release basically free H plus, not attached to anything else, floating around in the solution. And the amount of H plus that you have in that solution also determines whether or not the solution is going to be acidic or basic or neutral, for example. So acids are able to do that. And we think of acids really as sort of an ionic compound in a sense, even though traditionally they're really not. They're sort of covalently bonded. But in a sense, when they do go into solution, they're able to release that H plus, which then produces ions like we just kind of looked at there with the H2CO3, or release one H plus and make HCO3 minus. So the cation in all acids is H plus. So H plus is basically the positive guy in all acids. The anion is some type of negative ion, obviously. And in terms of naming acids, it's pretty much all comes down to our favorite element, which is oxygen, or maybe it's not your favorite element. Mine personally is selenium, which is Se. But oxygen here determines how we will name an acid. So if there is no acid, if there is no oxygen, we'll try that one better. If there is no oxygen in the acid, the way that the acid is named is hydro something ic acid. And the something there is the anion part, is sort of what fills in that name. Now, because what makes something an acid is the ability to basically produce these things in solutions, acids, when they write the formula, should always have aqueous next to it. And that is how you know it is sort of an acid. Aqueous means a water environment. Basically, it's a solution. So you took something and kind of dissolved it in water, for example, and you made a solution. So for example, if we have HBr, here we know this is an acid. We have aqueous. The cation is H plus, the anion is Br minus. And all we have to do is follow the procedure here. So this is going to be hydro. This is bromide. So this is going to be hydrobromic acid. If I have HCl, this is going to be hydrochloric acid, right? This is also why the aqueous is important. I think we talked about it. But if you had something that was HCl, say in the gas form, this would be called hydrogen chloride. Yeah, so that would be hydrogen chloride gas. And for example, if you take hydrogen chloride gas and bubble it through water, you perhaps get some hydrochloric acid basically happening in that situation. So that's why it's really important when you write formulas for acids that you do include the aqueous to imply that it is an acid. So for example, H2S here, what would that be called? It would be, so this is going to be hydrosulfuric acid. Now, in this case, we have two H's, and the reason for that is, again, we think of it like an ionic compound, which means the charge is equal to 0. So we know sulfur is group 6, which has a -2 charge, and we know that the H is H plus. So in this case, to balance it out, bless you, we do need 2 of the H pluses there to balance out the charge. So that works well. By the way, again, if you did not have the aqueous next to it, but had this, that would be hydrogen sulfide gas, which nobody wants to smell, especially if we go to 200B. Well, they took it out of 200B. You don't smell it anymore, so that's good. But that would be hydrogen sulfide gas. So again, that aqueous pretty much implies it's a solution and that you're dealing with an acid in this case. Any questions on no oxygen? So no oxygen, hydro something ic acid. Now let's talk about how we name it when there is oxygen involved. So if we have an acid that does have oxygen, so if our acid has oxygen, and the answer is yes, it will most likely contain one of your favorite things, which is a polyatomic ion. It will most likely contain a polyatomic ion. These are also sometimes referred to as oxyacids because they contain oxygen. Now, as we know, and as we just talked about, the polyatomic ions pretty much end in one of two ways. They either end in ate usually or ite. So that is going to help you determine how you should name the acid. So if you have an acid which has a polyatomic ion with it, and the polyatomic ion ends in ate, the acid name will be something ic acid. So for example, here, a little HNO3. NO3 is NO3 minus. And obviously H plus, which is the acid cation part here. NO3 minus is nitrate. So this would be nitric acid. Yeah. H2SO4. SO4 2 minus, which is this guy. And that again is why we need not one, but two of those hydrogens to balance out the charge. But SO4 2 minus is sulfate, which means this should be sulfuric acid. No hydro in this, yeah? So if it has oxygen, you should not be laying up hydro in the name. Hydro is only for acids with no oxygen involved. So my H2CO3 that we looked at a second ago, what should that name be? CO3 is what? CO3 is carbonate, which means this will be carbonic acid, yeah. How about HClO4? ClO4 minus and H plus, basically, right? ClO4 minus is perchlorate. So this should be what? The per stays. This is perchloric acid. Yeah. So if you have one of those polyatomic ions that has like kind of that either per or hypo in it, it still stays with the name. You just want to end it with the ic. Any questions on that? Good way to remember that is you ate too much, you feel icky. Yeah, so that's how the acid should go. Yeah, in that case. Now, if we have a polyatomic ion and it ends in ite, the acid name is something OUS acid. So now if I take HNO2, NO2 is NO2 minus and H plus. NO2 minus is nitrite. So this would be nitrous acid. What would H2SO3 be? SO3 is SO3 2 minus, which is what? Well, I know it's not sulfate, right? Has one less oxygen, which would make it sulfite, right? And then that would mean that this is sulfite, and that is what I was talking about earlier. If I know that's sulfate, one less oxygen should be sulfite, and that should be sulfurous acid, right? And a little HClO. What would the name of this guy be? That guy there is ClO minus, which is what? It is hypochlorite, ITE, which means it should then become hypochlorous acid. Acid there. So again, here with the ite, there is no hydro. So once again, you should not be using hydro with anything that has oxygen. That's an oxyacid. Specifically, really a lot of the non-oxygen sort of acids come from group 7 on the periodic table. Your HBr, your HI, your HCl, HF is kind of where those guys come from. Any questions on how to name acids? Yeah. It's good we're still doing naming. All right, the last, or close to the last type of naming that we're going to do is one that's sometimes classified as type 3. And type 3 compounds are 2 nonmetals together. And as we know, 2 nonmetals together basically means that we're going to be sharing electrons. And this is more of a covalent or molecular compound. Type 3, frankly, is the easiest one to name, but it's also the one people screw up the most on. Yeah, so this is really the one that most people will screw up kind of the most on. We talked about it, I think, but just in case we didn't, there are certain ones that should go, or certain compounds that should go by their common name, just to make sure. And a couple of those are definitely, or a few of those are sort of 2 nonmetals together. So H2O, as we hopefully know, is water. NH3 is ammonia, not to be confused with what we just saw there in our polyatomic ion, which is NH4 plus, which is the ammonium ion. So they are different. One's an ion, one is not. And CH4 is methane, which is the simplest organic molecule that you could have. So all other sort of nonmetals here, nonmetals, will follow type 3 rules. The good thing about this is, frankly, it is sharing of electrons, which means there's no charges, there's no ions. You don't have to figure out anything. And this is your long-awaited time where you actually do use prefixes. So this is the correct place to use prefixes when you're naming, is in this type of compound, and pretty much nowhere else. So prefixes should be put onto here. We will use prefixes like mono, which is 1. I think we have a table coming up. Di, which is 2. Tri, which is 3. Tetra, which is 4. Penta, which is 5. Hexa, which is 6. Hepta, which is 7. Octa, which is 8. Nona, which is 9. And deca, which is 10. So we use these prefixes here, and pretty much we use the prefixes to indicate how many of each of the elements we have. So it's pretty straightforward. Like I said, no charges or anything like that to try to figure out. So when we name these guys that are non-metal together, we name it based on the formula. If we have the formula given to us, obviously, we will take the first element first, followed by the second. And it goes the same way. If you sort of have the name, you'll just write the formula based on the first name and the second name. We use really the whole name. So we can use for this one the prefix plus the whole name of the first element. And then we will use a prefix, and the second guy will be named like everything else we've been doing. It will get the IDE treatment at the end. Now, there are a couple of rules and things that happen when we're dealing with type 3 sort of compounds. And that is, first off, one of the major ones is we do not use mono on the first name, but you can use it on the second name. So no mono on the first name, but it is okay to use on the second name. So we also will have, in a lot of cases, a couple of vowels that back up to each other. The ending vowel on the prefix and the beginning vowel there on the element name. So for example, we can get a couple of O's that sort of back up on each other when we go to name it. And we typically will get rid of the O on the prefix. Also an A and an O. Typically we get rid of the A on the prefix as well. So for example, here, that is C and O. C is carbon, which is a nonmetal. O is oxygen, which is a nonmetal, which means you're in type 3 category. All you have to do basically is name what's there. There's only one carbon, and the prefix would be mono, and there's only one oxygen. The prefix would be mono. Once again, here, we will not use mono on the first name, so we'll just use the whole name of the first element, which would be carbon. We can use mono on the second name. That would be mono, and the second guy becomes oxide. And in this case, if we did it directly like that, we would end up with carbon monoxide, and that's not really what we call it. We call it carbon monoxide, right? So we do get rid of the O, and we would call it monoxide in this case. So it's a good example of all those things sort of happening. Actually, a couple of I's that back up to each other, which can happen. It's actually okay. So it's mainly the OO and the AO that backs up to each other. And typically we drop it from the prefix. So we drop the letter there, or the vowel from the prefix. Any questions on that there? So there you go. There's our prefixes. And again, we do drop some of those last vowels. We also see it with tetroxide as well. Again, our tetroxide, we do drop the A from the prefix, so we don't get that A and O that backs up. And once again, that's the one we just did there. We dropped the O from the prefix as well. Here's our couple of guys, and once again, our methane going by our common name. So again, H2O is water. It is not dihydrogen monoxide, because again, nobody wants a refreshing glass of dihydrogen monoxide. Yeah, so just call it water and stuff like that. NAR is ammonia, nitrogen trihydride. So again, just call it ammonia. All right, so why don't you do a few of these here? Why don't you also write the formula for some stuff I'll make up? Let's go with nitrogen trioxide. Let's do okay, let's take a look at these. And really, as I mentioned, these really should be sort of the fastest ones that you come across. So what you want to look at is pretty much what you're dealing with. So I see I, which is a nonmetal. I see O, which is also a nonmetal. So that tells me it's type 3. I don't have to worry about charges or figuring out anything. Pretty much just need to pick the right prefix for how many it's there. So I have 2 I's, and that 2 prefix is di. So that's going to be a diiodine. We're going to use the whole name of the first element. Prefix for 7 there is hepta, and oxygen, which is the second element, should end in IDE. So this would be one, though, that we would get that AO backing up that we saw earlier. So we will drop the A off of the prefix in that case. and we'll end up with diiodine heptoxide. Also here again, the two I's are okay apparently for everybody, but the A and the O and the O and the O not so good. Any questions on that one? Same thing on the next one. I got carbon, which is a nonmetal. I got oxygen, which is a nonmetal. So again, type 3. We have only one carbon, which is mono. We got two oxygens, which is di. Once again, we do not use mono on the first name, so we're just going to use the whole name of it, which is carbon. And we will use di, and again, giving the oxygen the IDE at the end of it. So carbon dioxide in this case. Lastly here, we got one phosphorus, which is mono. We got three, which is tri. Here again, we won't use the mono on the first name, so phosphorus and tri, giving the chlorine the same IDE ending in that case. Any questions on any of those three? Probably the fastest of anything to do is the next set on the right. Here we have the name and we want the formula. So really, as soon as I see prefixes, I pretty much know what I need to do. Di is 2, nitrogen is N, so that's N2. Tri is 3, oxide is oxygen, O3. I'm done. I don't have to balance out anything. I just pretty much write what it says. Phosphorus with no prefix, but I do see hexa here, which is a prefix, so that tells me it is going to be a type 3 compound. So with no prefix, that means we just have one of them, right? Because we're not going to use mono on the first name. So we're just going to write P. Hexa is the prefix for 6, and Cl is chloride. So a little PCl6 in this case. Any questions on those there? Lastly here on this probably made up one, we got penta, which is 5, and chlorine. So that's a Cl5. We have a tetra, which is 4, and a bromine. Whatever the heck that is. All right, there we go. Any questions on any type 3? So like I said, probably the easiest, but really the one that people most often will screw up on because they want to do all kinds of weird things they shouldn't do. Again, here you see in type 3, there is no Roman numerals with it or anything like that. So this is the place where you should use prefixes. And as we talked about earlier, if you are Roman numerating and prefixing, it is probably wrong in most cases. Any questions on type 3? All right, last thing we're talking about is something that we talked about previously when we did the experiment, but we do come across sometimes hydrates, right? And as we know, hydrates basically have two parts. It has a salt part separated by a little dot and really a water part, right? And the water part is known as a hydrate. And we do use a prefix to indicate how many waters are there. The salt part is named as either a type 1 or type 2 ionic compound, because that's usually what it is. So we had our one that we did, which was MgSO4.7 waters, I think, in this case. And again, we would basically just name it like normal. A reminder that this dot here separates basically the salt part from the water part, and that's just the way hydrates are written. So that is a type 1 metal. So we use the whole name there, magnesium. That is a polyatomic ion, so we use the whole name there as well, sulfate. Here we have 7, and we use kind of the same prefixes we just looked at. That would be hepta and hydrate, right? If I have this, what would that be? Maybe I'll write it up a little bit higher here. All right, so what would this hydrate's name be? So it's close. So we take a look at this. This is the salt part. So that is a metal. That's a transition metal, which means, do I need a Roman numeral? I do need a Roman numeral, right? Because it could be copper 1 or copper 2. In this case, we know from knowing our polyatomic ions here that that is NO3 minus, and there's 2 of them, which gives us a -2 overall. That means that our copper here will be +2. So we still follow really the same kind of type 2 situation. The first part of this name should be copper Roman numeral 2, and we use the whole name of our polyatomic ion, regardless of how many there are. That'll be copper Roman numeral 2 nitrate, and as you correctly said, prefix there for 4 is tetra, and it would be hydrate in this case. Yeah. So really, hydrates, you name the water part as hydrate, and you name the salt part like you would do a type 1 or type 2 sort of compound. Any questions on how to name that? All right, that wraps up naming. You're now professionals. Congratulations. Yeah. We're going to then roll into the next chapter. But as a parting gift, next Tuesday, we will have a quiz on naming, just to make sure you're keeping up with this. So, all right, speaking of the next exam, chapter 5 should be, if I'm not mistaken, the last chapter that will be on the next exam that's coming up. So it's pretty much 3, 4, and 5, I want to say, is what's on there. So pretty much naming and geometry and Lewis structures. And now we're going to talk about grams, moles, and empirical formulas and molecular formulas, which will help us out with that lab that we did obviously last week. So we'll get through some of this here, and we'll see when that lab report will be due, before June, maybe. All right, so chapter 5 here. We're going to talk about grams and moles, but first we're going to talk about atomic masses. And atomic mass is the number that we do see on the periodic table. It is that number that is on the bottom there. And that is what is referred to as the atomic mass. As we talked about, that is not the mass number, like when we talked about those mass numbers and stuff like that. One of the fundamental properties of an atom is its mass. It's based on the number of protons, electrons, and neutrons. Obviously, atoms are extremely small, so you can't pick them up and just put them on a balance or anything like that to measure them out or weigh them. So usually in chemistry, when we can't sort of directly measure something, a lot of times we assign something as sort of a standard to sort of compare everybody to. And in the terms of atomic masses, they chose an isotope of carbon, which is the carbon-12 isotope, to basically compare everybody to. So the carbon-12 isotope has a mass of exactly 12, what is referred to as AMU, and that is the atomic mass unit, which is a unit of atomic mass, which frankly, after this little part section, we'll never use. And we will use a more convenient unit of mass, which is molar mass, which is grams per mole. So we usually will use molar mass because when we weigh out something on a balance, it's in grams. So that's a more convenient sort of unit that is used. As we will see, numerically speaking, the atomic mass in AMU per atom and grams per mole is actually the same. So it comes out the same in terms of the numbers like that. So basically what they said was 1 AMU is also sometimes referred to as a Dalton, but the carbon-12 isotope has 6 protons and 6 neutrons, and again, a mass of exactly 12 AMU. So you might wonder to yourself, you know, if you look at carbon, it doesn't really say 12, but it does say 12.01. And we will talk about in just a second here why that is. So, for example, they did experiments and showed that the mass of hydrogen, for example, is only about 8.4% as big as the carbon-12 isotope. And they basically did a little calculation there. That's basically 8.4% converted into a decimal, times it by the atomic mass of our carbon-12, gets us that 1.008 AMU that we see on the periodic table. Similar calculations were done for everybody that's on the periodic table. One way that you can use that number off of the periodic table is that there would be 1.008 AMU in an atom, would be the atomic mass for hydrogen. You could also do that for oxygen. When you look up there, basically a 16, probably say 15.9999. And that would mean that there is 16 AMU per atom for oxygen. So One way you can use it if you do want to calculate something in atomic mass units is you could use that as a conversion factor to convert between atoms and the mass of each of those things. As I mentioned before, when we look at carbon on the periodic table, it actually will say 12.01. So if our carbon 12 isotope has a mass of 12, why does it actually say 12.01? And that is because what we see on the periodic table are actually average atomic masses, and they're average atomic masses of all the naturally occurring isotopes for that particular element. So something like carbon has a carbon 12 isotope, also has a carbon 13 isotope, and they average sort of those masses together to calculate the atomic mass that we see on the periodic table. Most people don't refer to it as an average atomic mass, but it really is an average atomic mass of each of those naturally occurring isotopes. So one way that you could calculate the atomic mass, like you see on the periodic table, is you would take the percentage of the first isotope, and that is sometimes referred to as the relative abundance or percent relative abundance, basically the percentage that it occurs naturally in nature, obviously. You would times it by the atomic mass of the first isotope. Reminder that isotopes are the same element, right? But they have different numbers of neutrons, right? So they have different masses. You would then take the percentage of the second isotope and times it by the atomic mass of the second isotope. And you would continue this pattern depending on how many naturally occurring isotopes. The key is when people do this calculation, they screw up because they want to multiply, but it's actually adding here. So you want to add those guys together rather than multiplying. Obviously, if we had all the naturally occurring isotopes for a particular element, all the percentages should add up to 100%. Yeah. So clearly, if you're missing a percentage, you could subtract from 100 to figure out the missing percentage. You would have some type of information to do so. So this is basically the calculations that you do to sort of get the atomic masses that we see on the periodic table. By the way, as we hopefully know as well, we need to convert the percentage into a decimal, right, when we do the math. So you could either divide it by 100 or just move the decimal a couple places to the left, and that will do it for you. But you do want to make sure, obviously, you convert out of the percentage if you're going to do the calculation. Any questions on that there? So if we look at something like carbon as our example there, we see that there's basically the two isotopes of carbon. We have our carbon 12 isotope, which has a mass of 12 AMU. We also have our carbon 13 isotope, which has a mass of 13.00335 AMU. And from this, we can see that the carbon 12 isotope occurs roughly 99% of the time. And our carbon 13 is about 1.1% of the time. So if you just take a quick addition of those two percentages, it does add up to about 100. It may not add up perfectly to 100, maybe a little less, a little bit more, but it should definitely be in the 100 ballpark. So that is the calculation we just talked about. This is the percentage of our carbon 12 isotope converted into a decimal, and that is the mass of our carbon 12 isotope. Again, we're going to add it to the percentage of our carbon 13 isotope converted into a decimal times the mass of our carbon 13 isotope, and that is how we get to our 12.01 number that we see underneath there for carbon. It is important to know that you would never, if you could, sort of pick out individual carbon atoms. You would never grab one that has a mass of 12.01. You would either grab a carbon 12 isotope, right, which would have a mass of 12, or you grab a carbon 13 isotope that has a mass of 13 and some change. So there really is no sort of carbon guy that has an exact mass of 12.01. So again, those are average values that we can use, and they are based on the naturally occurring isotopes for that particular element. Yeah. Yeah, so there are variations on these type of problems. So for example, you may be given, say, the masses of both isotopes and maybe just one of the percentages. So you might have to subtract from 100 to get to that. You may actually just be given the atomic mass itself. And maybe, you know, you have the percentages in one of the masses of an isotope, and maybe you want to find the mass of a particular isotope. So you can, in certain questions, be asked to solve for really anything in that formula, either the percent abundance, which is sometimes what is referred to the atomic mass of individual isotopes, or just the atomic mass of the element itself. So to answer your question, yes, it's possible you could have a question that any of those things could be asked. Other questions? All right, so there is a relationship between atomic mass unit and grams. One atomic mass unit is equal to 1.66 times 10 to the minus 24 grams. Obviously, it's a very small number, that grams. All right. So as I mentioned before, probably not too much of these sort of calculations you will do in your chemistry career, but you can, again, use those numbers from the periodic table as a really conversion factor. So here's our carbon and our 12.01. And again, we could use it as 12.01 AMU per atom. R an atom is 12.01 AMU. So if we were asked what is the mass in AMU of 431 atoms of carbon, we would set it up with dimensional analysis here. Opposites cancel, so atoms on top, atoms on the bottom, gives us about 5176 AMU in terms of the mass of those 431 carbon atoms. So really, much like we use molar mass as well, atomic mass here is really kind of a conversion factor that you could use to go really from AMU to atoms, or atoms back to AMU, if you're looking for those units, which again, as I mentioned, probably fairly rare sort of a calculation that you would probably do in terms of atomic mass unit. If we look at aluminum, again, we will see 2698 underneath there, which means we really could get two conversion factors from that, 2698 AMU per atom. R an atom is 26.98 AMU. And in this case, we're looking for the mass, once again, of 75 atoms of aluminum. So setting up so our atoms cancel, leaves us with a mass of 2024 AMU. Any question on those calculations there? Just like writing stuff on my page. All right, maybe we'll move pages and I'll stop scribbling on the page there. Maybe get it. Let's see if that, there we go. So how can we figure out the sort of percentages of each of these isotopes and maybe their relative masses? One of the techniques that's used to do this is what's referred to as mass spec, or mass spectrometry. And basically, it is atoms that are ionized, sent down tubes where there's an electrical field and a magnetic field. And basically, that's able to sort of separate out the different isotopes based on their masses. And you'll also see basically different peaks or different heights of the peaks, which will give you kind of the percentages of each of those guys, of those isotopes that are present. And this is a typical sort of mass spec chart that you get out. These are our relative isotopes and our relative masses. And again, our relative percentages here. So roughly 75-ish, 25-ish sort of percent, around 100% of those chlorine isotopes coming out. So that is sort of how you can kind of figure out those percentages of those isotopes, and also, you know, the relative masses as they move down the graph. They'll be a little bit slower and sort of move off to the left, the lighter ones. So as the sample goes through, you heat it up really and ionize it. Goes through first an electrical field, and as we talked about when we were talking about the atom, obviously we can use the electrical field and a magnetic field to separate out things that have sort of charges. And as they come through here, they go through the magnet. And again, on the graph, kind of our heaviest guys end up to the right here on the detector, and our light guys kind of go there to the left. And again, that will sort of separate them out by the mass. And again, the relative sort of peaks that you see on the graph, again, will give you sort of your percentages that occur. So why don't you try this one? If copper is 69.17%, copper 63, and has a mass of 62.9396, and copper 65 has a mass of 64.9278. Okay, let's take a look. So we're given two isotopes of copper. So we have copper 63, and it occurs 69.17% of the time, and it has a mass of 62.9396 AMU. We also have copper 65 here that has a mass of 64.9278 AMU. Once again, here they did not give us that percentage of our copper 65, assuming probably correctly here in this case that there's just these two isotopes, so all the naturally occurring ones. We could get the percentage of our copper 65 by subtracting from 100%, right? So take 100% minus 69.17% gets us about 30.83%, which would be our missing percentage that we need for the calculation. Any questions on that? Now that we have really the percentage and the mass of each of these isotopes, we could go into our formula. So our atomic mass will equal our first isotope. I'm just going to move the decimal place 2 places to the left. So it's going to give me 0.6917% basically. We're going to times that by our mass of 62.9396 AMU. We are again going to add it here, not multiply, to our second isotope. Also, I'm going to move the decimal place 2 places to the left and times it by 64.9278 AMU. That is going to get us here. We got 0.6917 times 62.9396 plus 0.3083 times 64.9278. Going to give us something like 63.55 AMU, which I think is fairly close to what you see there for copper on the periodic table. Any questions on that calculation there? So again, this is basically the similar calculation as to how we get all those numbers there on the periodic table. Any questions? Okay, now that we talked about atomic mass, let's talk about really maybe some more usable sort of units that we use from the periodic table here. And that really is molar mass and our friend Avogadro's number. That's the one we just did. So they got the same answer. So that's good always, right? So let's talk about the idea of a mole. A mole in chemistry represents a certain amount of something. Just like in life, we have words that represent a certain amount. If we have a pair of something, that is 2. If we have a dozen of something, that is 12. If you have a gross of something, that's how much? 144. It's a good Jeopardy question, just in case it ever comes up. That's how they used to count pencils. They give you like a gross of pencils and stuff like that. When they used to give you pencils in school, they don't do that anymore, I don't think. But the mole, and by the way, this is the abbreviation for mole. So when you do see MOL, that is mole. They had to cut something off, so they cut the E off. But very common as well. Sometimes people, when they see MOL, they automatically think molecules, so they want to use it as molecules. But again, that is the abbreviation for moles. So make sure that you don't kind of confuse that. So a mole is the amount of elementary substances that there are in 12 grams of the carbon-12 isotope. 1 mole of anything will equal 6.022 times 10 to the 23. And you want to make sure, obviously, that you use your exponent button when you use this number. The units, though, that go with this number can change. So they may be particles, they may be atoms, they may be molecules, maybe particles, maybe pizzas as it's dinner time, shoes to go get your pizza and walk with, whatever it may be. Probably most of the time, except for the occasional pizza question, you probably will come across atoms and molecules as the units most associated with it. So always 1 mole of anything pretty much gives you that. That number is our Avogadro's number, right? I didn't say Avogadro's number, which I had a girl one semester, and that's all she said. So Avogadro's number. I'm like, I think by the end I was saying it as well. So Avogadro's number is basically 6.022 times 10 to the 23 in this case. So it does apply to anything. You could take anybody from the periodic table. So if I had 1 mole of hydrogen, that should have 6.022 times 10 to the 23 atoms of hydrogen. If I have 1 mole of iron, that also should have 6.022 times 10 to the 23 atoms of hydrogen or of iron. Also applies to things that are not individual elements, like if I had 1 mole of water, I would have how many molecules of water? 6.022 times 10 to the 23 molecules of water. If I had 1 mole of methane, I would have 6.022 times 10 to the 23 molecules of methane. So here we use molecules for water and methane because they are molecules. For individual elements, we use atoms as the unit, and that's again what we're talking about, that they can change. So really, from any of these, you could write 2 conversion factors that you could use. You can use for example, here you could say 1 mole of hydrogen would have 6.022 times 10 to the 23 atoms. Or you could use it the opposite way, 6.022 times 10 to the 23 atoms of hydrogen would be 1 mole. So we really use Avogadro's number as a conversion factor, basically to go between moles to atoms or molecules, or backwards, basically from atoms and molecules to moles. So this is what you want to use if you're doing either way conversion, is you want to use Avogadro's number to do that. You should not use Avogadro's number in every calculation because it is unnecessary in a lot of calculations. But sometimes people remember this number and go, well, maybe I should throw it in this calculation just in case. And usually you'll probably do it wrong. Or if you do it wrong the good way, a lot of times people will divide by Avogadro's number and then kind of multiply by Avogadro's number on the back end of the calculation. So no harm done, I suppose, except for extra writing. But the deal to know whether or not you should use Avogadro's number is really in the wording of the problem you're dealing with. So if you have any number that is given to you in that problem that's in atoms or molecules, you should use Avogadro's number. If you're looking for any answer that needs to end up in atoms or molecules, you should use Avogadro's number. If there's no mention of atoms or molecules in the problem anywhere, leave Avogadro's number on the side. Yes, so do not use it in the calculation. Any questions on that there? Now, the next conversion factor that we use really is probably the one that you use the most, and it's the most sort of useful one, and that is molar mass. And molar mass has units of grams per mole. And when we calculate the molar mass, it's always, the number stays with the grams, and it's always per 1 mole of the substance. And we calculate the molar mass really from the periodic table. It is the same thing that we use as the atomic mass. And as we mentioned a second ago, if you do the conversion, the atomic mass and the molar mass basically will end up being the same number. Avogadro's number, by the way, is the conversion factor to make that work on that conversion. So, for example, if we were to take hydrogen there, as we saw earlier, that could be 1.008 AMU per atom. but most likely we will pull it off and it will be 1.008 grams per mole. We can use this as a conversion factor of 1.008 grams of hydrogen in a mole of hydrogen, or again, a mole of hydrogen would have 1.008 grams of hydrogen. If you're asked what the molar mass of hydrogen, that would be the answer right there, 1.008 grams per mole. We could do it from anybody from the periodic table. We also could do it for things that are molecules or compounds, like water. If we wanted the molar mass of water, we basically just add up all the parts from the periodic table. So we have hydrogen. If we go up there, we will find oxygen. And basically here, it would be 2 times the molar mass of hydrogen plus the molar mass of oxygen, which gives us a molar mass for water of 18.02 grams per mole. Once again, we could use that as a conversion factor with the grams up on top and the moles on the bottom. Molar mass is used everywhere here in chemistry. It's pretty much the major one, probably more so than even Avogadro's number. Yeah, so Avogadro's number pops up occasionally, but not a lot, but molar mass and pops up a lot in chemistry. And it is your basic conversion factor to go from grams to moles or backwards. So that is your molar mass, and that's from the periodic table we get it from. Any questions on that? Typically speaking, when we go to the periodic table and we grab the molar mass from it, it's about 4 sig figs is typically the numbers that you should take. Depending on the periodic table you're looking at, you may have more numbers than that. So usually you round to 4 significant figures when we pop it off the periodic table there to use. Any questions on that there? So what is the relationship between Avogadro's number and molar mass? They are related to each other. So for example, if I have 1 mole of hydrogen, as we saw, that would be 6.022 times 10 to the 23 atoms of hydrogen. And that would be equivalent to 1.008 grams of hydrogen. So that is how they're all related to each other. Same thing with the water. 1 mole of water would be 6.022 times 10 to the 23 molecules of water. And that would represent basically 18.02 grams of water in this particular case. So if you need to go all the way from grams to atoms or molecules, again, you do need to use Avogadro's number to do that, and vice versa if you're going the opposite way. It is the moles that basically ties both of those things together, basically atoms, molecules, and grams. It is that moles in the middle that basically ties them together. And to get there may require Avogadro's number, or may require the molar mass to get the moles. But that's sort of the guide, the one that bridges basically both of those sort of units. Any questions on that there? We also talked about as well that you did have something like a hydrate that we were just talking about naming. You want to include the water, right, when we get the molar mass of everybody, like we did in those questions that we had, or that lab that we had. This is a mole of all these substances. Will 1 mole of different elements or substances, will they all look the same in terms of amounts? They will not, right? Because like a mole of sulfur is 3207, right? A mole of like copper, 6355. So they do represent a different amount of grams. We use molar mass basically because it is obviously a more convenient unit for what we sort of weigh out in lab. So here's the relationship between AMU and grams. And again, it's basically based off of Avogadro's number, but essentially numerically speaking, the molar mass and atomic mass is numerically the same sort of value. So there's our decision tree. And again, as you can see, as I was just talking about, it is the moles that basically tie kind of both ends of the spectrum together. So, and thinking of your pathway to get to wherever you want to get, you know, kind of think about where you need to go and then sort of where you need to end up with. All right, so why don't you try this one? Let's calculate the number of grams in 15.7 moles of iron. Iron is 5585, I hope. Still, look at the periodic table. Okay, let's take a look. So first off, we want to calculate the number of grams in 15.7 moles of iron. Do I need to use Avogadro's number here? I do not, because there's no mention of molecules or atoms or anything like that. So again, this is really a moles to grams conversion, and that is the molar mass from the periodic table that allows us to do that. When we pull that number off, that is 5585 grams per mole as the molar mass for iron. Gives us really, we could use it as a conversion factor so you can see where the units are so we don't make any calculation errors there. And in this case, we will start with 15.7 moles of iron. We want to get rid of moles, so we're going to use it just like this. You can set it up as dimensional analysis. So again, we can see the units and make sure we're multiplying when we want to, and perhaps divide when we want to. In this case, we're going to multiply, and that's going to get us 15.7 times 5585. Going to get us going to give us 876.845. And these would be grams. Sig fig wise, that's where you want to look. We'll consider this sort of an exact number. So that has 3 sig figs, maybe 877 grams of iron now. Would be a good number to go to. Any questions on that calculation there? Yeah. Let's take a look at one more here to finish it up. How many moles of lithium are there in 77.8 grams of lithium? Again, lithium, in case you don't have a periodic table, 6.941 would be the number that you would see there. All right, so to finish this one up here, once again, we really do not need Avogadro's number as there is no mention of molecules or atoms. A reminder that if you were asked this question and it did say MOL, that still is moles, so not molecules, so don't get that confused. So once again, this is going to be a grams to moles situation, which is the molar mass from the periodic table. It's going to allow us to do that, and that would be 6.941 grams per mole. And we will take our 77.8 grams of lithium. We want to go opposite, so grams are going to go on the bottom. Moles will go up on top, and the grams will cancel, so we're going to divide in this case, and that's going to get us 11.2 moles of lithium in this case when you do that. Any questions on that? One last thing about molar mass here to really finish up for today is, a very common mistake that people make sometimes is if they see an equation, and let's just say we had 4 waters, for example, and they wanted to calculate the molar mass for water, they oftentimes will try to take this number into account, and you shouldn't do that. So when you're asked to calculate the molar mass, or you need to calculate the molar mass of something, regardless, even if you have it in an equation and there's multiples of it, the molar mass is always calculated based on just the formula by itself. And that's why the molar mass is grams per 1 mole. So 1 mole of the actual substance. So you should always calculate it. So it would still be 18.02 here. Grams per mole would be the proper molar mass. You don't take that 4 into account. You take it into account when we talk about stoichiometry. Then you take it into account, but you do not take it into account